Namaste, my friend, and welcome back to JEE Mathematics with Typical Monk. This is class 4, and today the numbers start to move, not just sit there, but climb or shrink, following a rule. Here is something worth sitting with for a moment. A sequence is nothing but a rule for what comes next, and a series is simply what happens when you add all of it up. When Sarah first stared at a string of numbers on a test paper, she froze because she was hunting for a trick. There is no trick. There is only a pattern, and once you name the pattern, the whole series unlocks. Today, one idea at a time, we build the two patterns that run through the entire JEE syllabus, the arithmetic progression and the geometric progression, and then look at what happens when they meet. Take a slow breath. Let us begin. So what will you carry home from today's class? First, the arithmetic progression, its nth term, its sum, and how to insert arithmetic means between two numbers. Second, the geometric progression, its nth term, its sum, and the special case of an infinite GP. Third, the harmonic progression and the chain that links the arithmetic, geometric, and harmonic means. Fourth, the arithmetic-geometric series and the special sums of n squared, and n cubed, including telescoping. And fifth, the JEE drills, a worked problem, a match, and a short answer round. So everything you learn today, you can also score with. Ready? One idea at a time. Let us start with the raw material. A sequence is simply an ordered list of numbers, each one produced by a fixed rule, and every number in that list is called a term. David used to think a sequence was just a list someone wrote down at random. It never is. There is always a rule sitting behind it. A series is what you get when you add the terms of a sequence together, and we write that running sum as Sn. Same numbers, one is the list, the other is the total. The arithmetic progression is the simplest rule of all. Each term is the one before it plus a fixed common difference. The geometric progression multiplies instead of adding. Each term is the one before it times a fixed common ratio. Sit with that difference. Add for app, multiply for GP, because it decides which formula you reach for. Now, look at this figure, because it turns both progressions into a picture you can see growing. On the left, a staircase of bars, each one taller than the last by the same fixed amount, that is the app. On the right, a row of bars, each one scaled from the last by the same fixed ratio, that is the GP. First, the app's nth term, the first term plus n minus 1, lots of the common difference, one flat step at a time. Second, the app sum, half of n, times twice the first term, plus n minus 1, lots of the common difference. It simply pairs the first and last term and multiplies. Third, the GP's nth term, the first term times the common ratio, raised to the power n minus 1. Each bar is scaled, never added to. And fourth, the GP's sum, the first term times the ratio to the power n minus 1 over the ratio minus 1, valid whenever the ratio is not exactly 1. Lisa keeps them apart with one line, app adds, GP multiplies, and she never mixes the formulas again. Now we link two numbers three different ways. First, the arithmetic mean of two positive numbers, add them, and halve the result, the ordinary midpoint. Second, the geometric mean, the square root of their product, the midpoint of multiplication, rather than addition. Third, the harmonic mean, take the reciprocals, average those, then flip the result back over. It is the mean built for rates and speeds. And fourth, for any two positive numbers, the arithmetic mean is always greater than or equal to the geometric mean, which is always greater than or equal to the harmonic mean. John remembers the order alphabetically, A before G, before H, and that order never breaks for positive numbers. Time to solve a full problem together, slowly, the monk's way. Find the sum to infinity of 1 plus 3 times 1 half plus 5 times 1 half squared plus 7 times 1 half cubed, and so on forever. Step 1. Separate the two patterns hiding inside this series. The numbers 1, 3, 5, 7 are an app with first term 1 and common difference 2, riding on top of a GP with common ratio 1/2. Step 2. check that the sum to infinity can even exist. The size of the common ratio here is 1/2, which is less than 1, so the sum does converge. Step 3. Recall the formula for the sum to infinity of an arithmetic-geometric series. The first term over 1 minus the ratio plus the common difference times the ratio over 1 minus the ratio squared. Step 4. Substitute the numbers in. 1 over 1 minus 1/2 gives 2, and 2 times 1/2 over 1 minus 1/2 squared gives 4. Step 5. Add the two pieces together. 2 plus 4 gives 6, and that is the sum to infinity. Notice the path, split the app and the GP, check convergence, record the formula, substitute, add. The same steps unlock every arithmetic geometric series JEE can ask. Now, look at this second figure, because it explains why some series settle down and others never do. On the left, a sequence of shrinking blocks, each one half the size of the last. On the right, 3 stat bars showing how the 3 means compare. First, an infinite GP only has a finite sum when the size of the common ratio stays below 1. Otherwise, the terms never shrink and the total runs away. Second, each shrinking block adds a little less than the one before it, and the running total creeps toward a fixed ceiling, the sum to infinity. Third, for positive numbers, the arithmetic mean sits on top, the geometric mean sits in the middle, and the harmonic mean sits at the bottom. The ladder never flips. And fourth, all 3 bars shrink to the exact same length only when every number in the list is equal. That is the one case where the ladder collapses flat. SAR's test for convergence is this one line. If the ratio size is at least 1, stop. There is no sum to infinity. Now sit up straight. These 5 lines are what JEE actually asks year after year. 1. The sum to infinity of a GP only exists when the size of the common ratio is strictly less than 1. Always check this before you reach for the formula. 2. Never mix the two families. An app adds a common difference. A GP multiplies by a common ratio, and mixing them is the single most common slip in this chapter. 3. The nth term formula always uses n-1 steps away from the first term, forgetting that -1 is the classic off by 1 error. 4. The arithmetic mean is greater than or equal to the geometric mean, which is greater than or equal to the harmonic mean, with equality only when every term is equal. 5. The special sums of n squared and of n cubed often hide inside one longer series, and splitting the series into these pieces is usually the fastest route to the answer. Let us drill the JEE way. I read a claim, you decide true or false, and if it is false, find exactly where the reasoning breaks. First claim, the sum to infinity of a GP with common ratio 2 equals the first term over 1 minus 2. Let us check. The formula for the sum to infinity only holds when the size of the ratio is less than 1, and 2 fails that test completely. The series does not even converge. So this is false. There is no sum to infinity here at all. Second claim, the GP sum formula still works when the common ratio equals 1. Think carefully. That formula divides by the ratio -1, and when the ratio is exactly 1, that denominator becomes 0. The formula breaks down completely. When the ratio is 1, every term is identical. So the sum is simply the first term multiplied by the number of terms. This is false. The standard formula needs the ratio to differ from 1. Third claim, for any two positive numbers, the geometric mean squared equals the arithmetic mean times the harmonic mean. Check it directly. The geometric mean squared is just the product of the two numbers, and the arithmetic mean times the harmonic mean also simplifies to that same product. This one is true, and it is a beautiful identity worth remembering on its own. A quick match now. Say each answer aloud before I reveal it. 1 plus 2 plus 3 and so on up to n. That sum is n times n plus 1 over 2, the oldest special sum in the book. 1 squared plus 2 squared and so on up to n squared. That sum is n times n plus 1 times 2n plus 1 over 6. 1 cubed plus 2 cubed and so on up to n cubed. That sum is exactly the square of n times n plus 1 over 2. The cube sum writes on the app sum. and a GP that runs forever with the size of its ratio below 1, its sum to infinity is the first term over 1 minus the ratio. If all four came to you before the reveal, these special sums are becoming yours. Here is a favorite G format. I read some statements, you silently count how many are correct. Statement 1. The sum of the first n odd numbers is n squared. Hold your verdict. Statement 2. A GP with a negative common ratio can never have a sum to infinity. Think before you answer. Statement 3. The harmonic mean of two numbers is the reciprocal of the average of their reciprocals. So, how many are correct? Two statements, the first and the third. The sum of the first n odd numbers really is n squared, and the harmonic mean really is built exactly that way. But the second one falls. A negative ratio is completely fine as long as its size stays below 1. The sum to infinity still exists. Two correct statements 1 and 3. Now let me save you some marks. Two myths that trap thousands of students every year. Myth 1. The nth term of an app is the first term plus n times the common difference. It feels natural. Term number n, so multiply by n, surely. David believed this for weeks. But here is the truth. The nth term is the first term plus n minus 1 times the common difference, because the first term itself has taken 0 steps. Miscounting that one step throws off every term after it. Myth 2. The sum to infinity formula works for every geometric progression, no matter what. The truth? It only works when the size of the common ratio is strictly less than 1. Outside that range, the series either grows without bound or oscillates, and there is no finite sum to find at all. Time to test yourself. Rapid fire. Here is the rule. I ask, you answer in your head before the reveal. No pen, no paper, just the ideas you built today. Question 1. What is the sum of the first 20 natural numbers? 20 times 21 over 2, 210. Question 2. What is the 10th term of the app 4, 7, 10, 13, and so on? 4 plus 9 times 3, 31. Question 3. What is the sum to infinity of a GP with first term 6 and common ratio 1/3? 6 over 1 minus 1/3, 9. Question 4. What is the geometric mean of 4 and 9? The square root of 36, 6. And question 5. What is the fifth term of the GP2, 6, 18, and so on? 2 times 3 to the power 4, 162. If you caught all 5, you have truly understood today's class. Let us gather the whole class in one slow breath. An app grows by adding a fixed common difference, its nth term and its sum both lean on that one constant step. A GP grows by multiplying a fixed common ratio instead, and its sum formula needs the ratio to differ from 1. An infinite GP only has a sum when the size of its ratio stays below 1, and that sum is the first term over 1 minus the ratio. For positive numbers, the arithmetic mean sits above the geometric mean, which sits above the harmonic mean, and the geometric mean squared always equals their product. The special sums of n squared and of n cubed, along with telescoping, collapse long ugly series into one tidy closed form. And next class, we step into permutations and combinations, counting, arranging, and choosing, the fundamental principle that runs through the entire chapter. Do not miss it. And so, my friend, we have taken another step forward. It may have looked like just letters and formulas, but understand this: every pattern you will ever meet in this course, from a distant future series to a simple loop in a computer program, is built from exactly this idea, a rule for what comes next. Sarah, David, Lisa, and John all once stared at a string of numbers and felt lost, exactly like you might feel right now. Be patient with yourself. Tonight, revise the difference between adding and multiplying, once, slowly, because that one distinction carries this entire chapter. One idea at a time, you'll crack G. Of this I am certain. If this class brought you clarity, subscribe to the channel so the next one finds you. Until then, keep going. I will see you in the counting chapter.